All right, let's dive in. If you're gearing up for a quant roll, you already know that probability is basically the name of the game. Today, we're going to level up from the basics and tackle two massive concepts: functions of random variables and joint distributions. Let's get to it. So, you've probably nailed questions about a single coin flip or one die roll 1,000 times over, right? But the real world, and especially the financial markets, are just never that simple. The value of an asset isn't just one random number, it's being pulled and pushed by dozens of other variables. So the big question is, how do we even begin to handle that kind of complexity? Well, the first step is a mental shift. We need to stop thinking just about a random event and start thinking about a value that's derived from that event. And this is exactly where functions of random variables come into play. Trust me, this idea is at the absolute core of pricing pretty much any kind of derivative out there. Okay, let's stick with our simple die roll for just a second. Imagine you're in a game where your payout isn't the number you roll, it's the square of that number. So if you roll a 2, you get $4. You roll a 5, you get $25. See what's happening? The outcome of the die, that's our first random variable. But the payout? That's a totally new one, and it has its very own unique probability distribution. So here's how we map it out formally. Our die roll is X, our payout is Y. And that little function that connects them, g of x, is just x squared in our game. We're using the probability of x to build an entirely new probability map for y. What we're really doing here is adding a powerful new layer of analysis on top of a simple random event. So how do we actually find that new probability map for y? It's this really elegant three-step process. First, you start with the cumulative distribution function, the CDF, of our original die roll, x. Next, you apply the inverse of your payout function, so in our case, that's the square root. And for the final step, you differentiate that result, and boom, you've got the probability density function, the PDF, for y. It's an amazing mathematical toolkit that lets you transform one probability space into a completely different one. Okay, so we can now transform a single random variable. But what happens when we've got two variables happening at the exact same time? And that brings us to our next monster concept, joint distributions. You know, think about it. A stock's price doesn't move in a vacuum, right? It's influenced by interest rates, by market sentiment, by what its competitors are doing. The list goes on and on. To model this, we absolutely have to know how to handle multiple random variables at once. So let's go back to our simple analogy. How do we map out all the possibilities of rolling two dice at the same time? Now check this out. What you're looking at right here, this table is the joint distribution for two dice. It's the whole shebang. It's a complete map of every single possible outcome, from rolling a 1 and a 1 all the way to a 6 and a 6. And since each specific combo has a 1 in 36 chance of happening, this table captures the entire probability space of both variables together. All right, so now that we have this complete map, this joint distribution, what if we only care about one of the dice again? Can we get back to the simple single die probability from this more complicated picture? You bet we can. And that's exactly where marginal distributions come in. Now, this sounds super formal, but it's really simple. It's just a way of saying we're going to forget about one of the variables so we can focus on the other. So if you want the probability distribution for just the first die, you literally just sum up the probabilities in each row of our table. That gives you the marginal distribution for die 1. It's like looking at the whole picture from the side. And this brings us to the most important shortcut in this whole area. If your two variables are independent, and that's a big if, meaning the outcome of one has absolutely zero effect on the other, just like our two dice, then you don't even need to build the whole table. The joint probability of any two outcomes is just the product of their individual or marginal probabilities. It's a game changer. Okay, we've gone from one die to functions of one die to two dice and then back again. So why does any of this abstract math actually matter? Well, because these aren't just abstract tools. These are the things you will use every single day in a quant roll. Seriously, think about it. An options payoff is a direct function of the underlying stock price. That's our first concept, right there in action. The risk of your entire portfolio, it's not just the sum of the individual risks. It is completely determined by the joint distribution of all the assets inside it. Do they move together? Do they move independently? Or do they move in opposite directions? Answering that question is the key to diversification and to modeling the entire market. So I'll leave you with this final thought. Mastering these concepts gives you the framework to model incredibly complex systems. So if you could have a perfect, godlike understanding of the joint distribution between any two variables in the financial world, say oil prices and airline stocks or interest rates and the S&P 500, which one would you choose and why? That's the kind of thinking that separates a good quant from a truly great one.